Welcome to this meeting or to this session. In this session, we're going to discuss the second hydrocarbon, the alkenes. The alkenes are sometimes known as the olefins, and what makes the alkene distinct from other hydrocarbon is the presence of the double bond. This is an example of an alkene with a series of many carbon-to-carbon double bond. You are familiar with this. This is the beta-carotene. The beta-carotene is one of the precursors of your vitamin A, and this is found in carrots. From the prefix carrot that was taken from our vegetable carrots. So this is the vitamin A present in carrots. If you're going to look at, do not be scared as of this time because if you're going to look at this, it is just simply the same. Half of this is just a repeating unit of series of 1. If you're going to notice, you have this structure here and you have also this structure here. Another is you have this metal here and two metals here. So if you're going to look at this is just a mirror from here to there, it's just a mirror to the other side. It seems so lengthy, but it is just a mirror, a repeated mirror of one half of the structure. These are some drawings or illustrations of double bond that you could see that the structure represents some cartoon characters or some illustrations that an artist could show how these alkenes look like. And then the trivial name, you have Old MacDaniel Menunol, because this seems like an old man, a farmer at that. But the suggested chemical formula, take note, suggested chemical formula is as long as this. This is just simply naming hydrocarbon for fun. So you have here, it looks like a cow, it looks like a turkey, a sitting boss, a snake, serpent, and then you have also a long neck here for your giraffe, and then you have the duck. I repeat, this is just for fun. Okay, this is how the haloalkane could be illustrated in terms that we are going to have some transition on hydrocarbon alkane to alkene. So as a review, these are your alkanes. So again, your alkene seems similar with the alkanes, only the alkanes has single bond, but the alkenes has double bond. There are different classes of alkenes, or where the double bond is positioned. You have the terminal alkene, wherein the double bond are placed at the end, just like your bus terminal, the end of your travel. And then you have internal alkenes, wherein the alkenes are found at least at the center or after one carbon atom. And then you have cycloalkenes. These are the alkenes that could be found in your aromatic substances. So these are examples of classes of alkenes to illustrate your terminal alkene and then to illustrate also your internal alkene. So from here, This is your terminal carbon. This is your second carbon. So you could see here the double bond. It is part of the internal carbon. And then of course for your cycloalkenes, you have there the aromatic compound with the double bond. Just like in the example of terminal alkene, you could have here the double bond, and in the internal alkene, you could also have here the double bond and also the double bond here. For the cycloalkene, you could have anywhere between the carbons to have the double bond. And then this is the structure of the hydrocarbon alkane. The spatial arrangement around carbon-to-carbon bond is planar. The angles are 120 as compared to the methane. And then these are the molecular or cloud structure for alkenes. So if this is the alkane CH4, this is an example of the alkene CH3, CH3. So this is one carbon, this is one carbon. The yellow-green cloud or lobes represents the p orbitals, or the two p orbitals rather. So that if this is one CH3, the lobes here will be bonded with hydrogen. So this one will be bonded with another CH3. So you have here this this lobe will be attracted to here. So forming your sp2 orbital, and then resulting to a sigma bond. So this is your alkene. So you have here the first pp bond, the blue, this one is your first pp bond, and the green lobes will form your second bond that makes the double bond. So this is how it could be illustrated. This is your pp band, and that is your sigma band. So if you could recall, your CH3 has two p orbitals in this manner. So again, as a review, if these are your carbon and carbon, if hydrogen will play with them, the hydrogen are positioned in this manner and resulting to a geometrical structure. You have here your carbon, the blue lobes, and then you have also another carbon here, the another pair of blue lobes. Now for the hydrogen, you have here the gray circle, and you have here the hydrogen, the hydrogen. So this is the hydrogen for the first carbon. And for the second carbon, you have here the hydrogen, and you have here the hydrogen. The first band represented by the blue, and the second band, the covered, it is already covered, but that is actually the yellow-green sigma band. Okay. Your ethylene is shown in this condensed formula. In the ball and stick formula, it is illustrated as this. And then for the electron cloud formula, you could illustrate it as this. Okay, let us try to look into the double CC band, the properties of double CC band. Now, since the double CC band has two sticks, more or less, it is harder to move. So there is a restricted motion. And then the rotation only occurs if one of the sigma band, if you recall the blue loops, if one of which will be destroyed or broken or reformed in the process that is unfavorable, then the double CC band will become single CC band. And then another property is its capability to do stereoisomerism. Whenever two groups on each end of a double CC band are different from each other, two di astero, stereomers are possible. Sorry. You have the cis and trans butene. This is the butene. This is the cis butene that we are referring to, and at my back is the trans butene. So you have here the double band. Both carbon here are placed in one plane, so it is called cis. Here you have the double band. The first carbon is at the other side, and the next carbon is also at the other side. So this is trans butene. And then in terms of stability, trans alkenes are generally more stable than cis alkenes. So this is more stable as compared with the cis. And then let us try to look into the structure and bonding. The bond dissociation energies of the carbon-to-carbon bond in ethane is a sigma band, one sigma band only. In the case of ethylene, it has one sigma band for the green lobes and one pi band for the blue lobe. So ethylene can be used to estimate the strength of one sigma band component of a double bond. So if we are going to look at a carbon-to-carbon single bond, if one sigma band is equivalent to 88 kilocalorie per mole, or it requires this kind of energy, then uh, for the case of double band, it is 152 kilocalorie. It is higher than this because it has both sigma and pi band. So from here, we could determine that the energy for the pi band is 64 kilocalorie per mole. The 152 kilocalorie per mole is standard. It is given. And then we have here another for cycloalkenes. Cycloalkenes having fewer than 8 carbon atoms have cis geometry. Take note, if fewer than 8, the carbon atoms has cis geometry. A transcycloalkene must have a carbon chain long enough to connect the ends of the double bond without introducing too much strain. Now, in the case of transcyclooctene, so here you are referring to cis geometry. Now, let us try to look also the trans geometry. For example, the transcyclooctene is the smallest isolable transcycloalkane and is considered less stable than the cyclooctene, thus making few alkenes having higher energy trans isomer. And then let's go to your exercises, the IUPAC naming of alkenes. I repeat, as of this time, you should already be well versed with your alkanes. Naming of alkanes requires your skill in order to be able to name alkenes. Because the process of naming alkanes is more or less the same with that of alkenes. Okay, so you have here an example of a hydrocarbon with a double bond. So the book says, give the UPAC name of the following alkene. First rule, find the longest chain that contain both carbon of the double bond. So it claims that this is the longest bond. And it has 1, 2, 3, 4, 5, 6 carbons. So it is hexene. You just simply, if this is just all single bond, it is hexane. But with the presence of a double bonder, you remove the ane and change with in. Okay? And then when you had known the longest chain and had uh, observed that there are some alkyl groups, you identify what are the alkyl groups. Now, how are we going to position the numbering of carbon? Number the chain, and name using the first number assigned to the first carbon-to-carbon bond, the first CC double bond. So since you can see here the double bond, I think this is nearer, the carbon here is nearer to here rather than the carbon here. So we're going to assign this as the first carbon, second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. Now, next, we observe that we have methyl here, we have methyl, we have methyl. So all is methyl, and there are 3 methyl. So where are the 3 methyl? They are found in the second carbon. So 2, 3, 5, trimethyl, 2, 2, hexene. You could also do some cheating. Okay, but before I'm gonna tell you how to make a shortcut on naming, let us make some simple exercises. So, why is this called nonene? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 carbons. So it is nonene. The double bond is found here, and the nearest carbon terminal is also found here. So carbon 1, carbon 2. I repeat, numbering of the double bond is where the carbon is facing the double bond. So do not claim that this is the one holding the double bond. The double bond is at its back. The rule says it should be in front. So you have 1, 2, nonene. Okay. We have also another 2 nonene. Why 2 nonene? There are 9 carbons with double bond. Where is the double bond? At the second carbon. It is at the second carbon because the terminal carbon here is nearer than the carbon here. So numbering does not mean from left to right. Numbering of your carbon is dependent as to where is the nearest terminal carbon that is from the double bond. Now in this case, you have 1, 2, 3, so this is 3 nonene. This is also 1, 2, 3, 3 nonene. 1, 2, 3, 4, 5, 6. Of course, 6 has a greater number, implying that it is more away from the double bond. Now, we have here the presence of alkyl group. There are 2 carbons, so this is ethyl. So, how are you going to name, how are you going to name that? Let us try to review again. If single bond, it is ane. If double bond, it ends with in. If there are 2 double bonds, you write there adiene. Next, you look for the longest chain that contains both atoms of the double bond. So you look after identifying whether it is an alkene or alkene, you write adiene, and then you look for the longest carbon chain where you can pass the double bond. So if it is 3 carbon, you write there triadiene. Or no, that is not, that is 1, 2 diene. Were you able to get that? So if you're going to look at one example here, that is 1 carbon, 2 carbon, 3 carbon, 5 carbon, assuming that this is just simply H, not OH. So you have 1, 2, 3 carbons because that is O. It is called propene. Where is the carbon? This is another story. It is, your counting should be from the OH rather than from the double bond. There is the OH, this is carbon 1, that is carbon 2. Okay, for a more clear illustration, there's a double bond, so you can write now in. There are 2 double bonds, so we could write now a diene. You have 1, 2, 3, 4, 5. You have here 1, 2, 3. So it's safer to write this as your carbon 1. So this is 1, 2, 3, 3, 4, 5, 6. That is 6. So we could write now 3, 6 diene. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons decane. So this is decene. But how about if there is an attached alkyl group that is 1, 2 containing 2 carbons? So this is ethyl. I repeat, there is the presence of double bond, two double bond actually, positioned at 3 and 6 carbon. We started counting here because the nearest terminal carbon to a double bond is in this place. Not here because 1, 2, 3, 4 is longer than 1, 2, 3. Okay? Next, to consider, it is also possible that the methyl group could be found here or could be positioned here. Or you could also have two alkyl groups okay. So this is your example that is actually tricky. There is a double bond there, so you could write in. You have carbon 1, 2, 3, 4, 5, 6, 7. 7 only. But if we're going to come here, 1, 2, 3, but the problem is, if we're going to look at this, all of which are single bond. So this is not the longest chain, yung merong colored portion. So numbering, I repeat, always start where you could pass the double bond. If we're going to count here, that is really the longest carbon chain, but we are not passing the double bond. So this is the longest carbon chain that had passed the double bond. Are you able to get that? I repeat, do not take the longest chain. Take the longest, but rather look for the longest chain that passes through a double bond. Because the longest carbon chain might only be passing two single CC bonds. But if there is a double bond, you look for the longest carbon chain with a double bond. So the longest carbon chain is not 8, but rather 7. So it is double bond. You write there in, and then there are 7 heptane, so heptene. And since the double bond is found in carbon 1, you could just simply write heptene. But if it is in the second carbon, 2 heptene. So you could omit writing the number if it is 1. But placing the number is also correct. Okay, we do not stop there because we have an alkyl group here. So we have to recognize the alkyl group with 2 carbon, that is ethyl, and it is found in the second carbon. So you have there 2 ethyl, 1 heptene. Heptene, double bond. Heptane, the longest carbon is 7. The double bond is found in 1. And then you have also alkyl group ethyl, and it is found in carbon 2. The numbers refers to where carbon is this attached with, or is where the double bond is placed. Okay, let us take some more examples. Okay, For aromatic compound, in this case, we can see here double bond. So you write there in. There are 1, 2, 3, 4, 5. So it is pentene. And since it is aromatic, you write the prefix cyclo. So meaning to say, there are 5 carbons in the ring, or it is an aromatic compound with 5 carbons. So cyclopentene. And we have here also an alkyl group with 1 carbon. So you have methyl. Why number 1? It is the position of the double bond. And also likewise, it is found in the methyl is found in carbon 1. So the complete name could be 1-methyl 1-cyclopentene. But you could write this already as 1-methyl cyclopentene or just simply methyl cyclopentene. Okay, another example. We have here again a double bond. So you write there in how many carbons? You have 1, 2, 3, 4, 5, 6, 7. So it is a heptene. It is aromatic, so it is cyclo. And then it has an alkyl group with 1 carbon, methyl. At what number? Carbon number 3. Where did we count? From the first double bond. So you have here carbon 1 facing the double bond, 2, and then 3. That is the counting. Okay. Now, you might be asking the question, why did we not have to go this way? 1, 2, 3, 4, 5. No. Counting could starts from the double bond carbon going towards the nearest alkyl group. It is just like in this case. It is not 1, 2 methyl, but rather we started here numbering because the methyl is already found in carbon 1. So we do not go there. We start where the nearest alkyl group is present. Just as the same here. We do not start counting 1, 2, 3, 4, 5, 6, 7, but rather we count the carbon as starting from the double bond nearest, going towards the nearest alkyl group. Okay, so it is called one. It is called 3-methyl cycloheptene. Now, you might be imagining now, how does 1,6-methyl cyclohexene looks like? Now, you are thinking that it is made up of double bond. So, dapat may double bond. It is hexene. So, meron siyang 6 carbons in its aromatic structure or in its ring. Now, meron siyang alkyl group, methyl. Di, dalawa. But where are these? They are found in number 1 and 6. So you are sure that in the first, in the double bond, the first double CC bond, yung kanyang first carbon, merong methyl. As you go down to the carbon 6, you have also another methyl. So, is this the one that you have in your mind or you have written? So I repeat, meron siyang double bond because it ends with in 6 hexane, aromatic. So we have to draw with 6 corners for the carbon. Now, how, how do we count? You have here the carbon, double bond. So this is 1, 2, 3, 4, 5, 6. Now, why did we started here? Because we assume that the first methyl group is stayed with carbon 1. So this is carbon 1. We do not go here because this is a single bond, single bond, single bond, single bond. And counting should be passing first the double bond. So you have there 1, 2. The first methyl, and then 2, 3, 4, 5, 6, 6 carbon for the other methyl. Okay, these are illustrations of your alkyl group and their common name. This is the methylene group, the vinyl group or the ethyl group. The propyl group is also called as the alkyl group. This is the classic way of naming alkyl group. So there is your methylene group. So you could write here, uh, since it is a double bond, the longest chain is methylene cyclohexane. The longest carbon chain is not this one. The longest carbon chain is the aromatic compound, which are all single bond. So you write there ane, hexane, it is aromatic. And the double bond here is just simply an alkyl group, attaching an alkyl group. So since it is only one, you write there methylene. So methylene cyclohexane. And then vinyl. So in this case, it is 1-vinyl cyclohexane. This is again a review as to how to write the formula. Aromatic compounds also have double bonds, but not all with double bonds are alkene. An example is in front of you, the benzene ring. Okay, these are isomerisms of alkenes. Isomerisms in a way that they have the same number of carbons, same number of double bond. So this has 5 carbons, 5 carbons, 5 carbons, same double bond, isa lang, only one double bond, only one double bond. But these are different species of 5 containing carbon that is an alkene. Again, we would like to make an emphasis that you have here the cis structure and this is the trans structure. Okay, these are also some ways of naming. You might be encountering the letter C. It is actually Susamen, and then E for antigen. For C, they are placed on the same side of the CC band. For antigen, they are on the opposite side. So for trans, they are in the antigen form, so they are in a letter E. If it is in cis, then they are in the sustamen. Okay, this is how your alkane moves. So that is your ethane. So you could see here that the carbon could easily maneuver its movement. But in case of double bond, it is more restricted. So you consider the illustration. Okay, so you can see here the existence of the cis and trans or with more double bonds. These are the physical properties of alkenes. So they have their different boiling point and also melting point, but generally increases with molecular mass. So the heavier the alkene or the longer the alkene, the higher is the melting point. Alkenes are non-polar, so they are not miscible with water. Those are the simple explanations as to how they look like in terms of physical reactions. Now let us go to their chemical properties. So we could have the electrophilic addition mechanism. Of course, you have your electric addition mechanism in alkane. The principle is just the same. So if we say electrophilic addition mechanism, it is actually getting the carbon getting one hydrogen. So examples includes hydrogen halides and also concentrated sulfuric acid as uh, electrophiles. So the electrophile having some positive character is attracted to alkene. Ito yung electrophile. This is the alkene. The objective of this is to react with this. So if you're going to break the double bond, that is one electron, another electron here. So one of the electron will be attracted with the positive, or one of the electron will be attracted with the negative. So then therefore, if that is the case, this one could go here and this one could go here. Okay? That is the illustration. And then you have also electrophilic addition of hydrogen bromine. So this is now a halogen. The same principle, this one should be broken so that uh, the electron here could go with the hydrogen, and then since the electron here is free, then the negative electron, the halogen, could merge with it, finally having the product. Now we have also electrophilic addition by hydrogen bromide. So this red here will now be your bromide. Same principle. This will be broken. The first electron will be taken by hydrogen, and the next electron will be taken by bromine. And then electrophilic addition by hydrogen bromide. So last time it is BR-BR, now you have hydrogen bromide. Same principle will follow. So if you're going to look at a step-by-step procedure, this is the case. And then we have electrophilic addition of bromine. So we have there the illustration. Same principle. The double bond electron will be broken in order to give way for a positive and negative electron accommodation. Okay, we have also electrophilic addition of sulfuric acid. Again, the hydrogen of the sulfuric acid will go with one of the electron of the alkene, and the sulfate will go with the other carbon. And then you have also physical addition reaction using catalyst or high pressure. And then you have also electrophilic addition to propene. So in this case, two, there are now one, two, three carbons. While there are three carbons, still the one that actively plays with the addition are the carbons within the double bond. The other carbons do not play with the addition. So no matter how long is this tail, only this one are changing because only this one are working with the addition, the electrophilic addition. So we have the Markov-Nikov's role. In the Markov-Nikov's role, the electrophilic addition to alkene, the major product, is formed by a stable carbocation or the presence of carbon ion. So if this is the methyl group and you change this with one carbon, that makes it as a primary carbon with only one carbon attached. And then you have also here uh, secondary carbon having two carbons attached. And then tertiary carbon, you have one, two, three carbons attached. So this one is directly working with whatever carbonium ion is to be introduced. So this is an unsymmetrical Markov-Nikov's role illustration. And then we have addition polymerization. So forming already a polymer. So the one that will be attacking here is a polymer. So the polymer could be as long as this or could just be simply as short as this. And then you have also addition polymerization. So the big polymer will be attached to the uh, double CC bond. Then another thing that you should know after the different reactions, physical and chemical reactions, the next is preparation of alkenes. So we have elimination, we have dehydration. So how to prepare alkenes? You can prepare alkenes from elimination process from the halogen alkenes. So this is the equation. So here is your halogen, Br, the bromine. So this is your halogenoalkanes. How are you going to do elimination? Addition of alcoholic sodium hydroxide. And it will form the CH3H6. This is the propene. Of course, you have byproducts, water, and sodium bromide. And then from dehydration of alcohol. So if in this case you are working with halogenoalkanes, and another way of preparing is dehydration of alcohol. So this is the alcohol. It has two carbons, so this is ethanol. So this alcohol will be forming double bonds with the presence of sulfuric acid or any form of acid. So the dehydrating substance are sulfuric acid. For halogenoalkanes, it is the alkaline sodium hydroxide. So from here, you could make some distinction. If there is a preparation of alkene coming from halogenoalkanes, we'll make use of alkaline substances like sodium hydroxide. But if you are preparing alkenes from alcohol, you make use of acids. And then these are foundational illustration of formulating some synthesis. So these are examples of alkene preparation. I hope you can get the changes. And then we have here some review. So all the rest are actually illustration as to how addition, how preparation of compounds are present. So you could make this as your review chart or cheat chart. So here you have the addition of bromine. This is if it is addition of bromine, that is uh, preparation from halo alkanes, and then you have here sulfuric acid. So this is preparation from an alcohol. So if this is the double bond, it will all go to single bond. Of course, this is double bond, so it will form another two new bonds. So in this case, you have there the H and the X in the other uh, electron of the double bond. And in this case, you have X2, so you have there X and X. This is X and then water. Okay, this is stereochemistry. So this is still hydrohalogenation, that is the addition of a halide. So from the previous chart, this is illustrated as one way of preparing uh, an alkene from an alkene. So this is from an acid. Then this is the hydration. Again, these are illustrations as to how a aromatic double bond is working with halogens. In this case, you have representative from the Cl group and the bromine group. So a halogen plus water, you have to write their halogen and then OH for water. This is the step-by-step formation. When I was still a student, this is how we had illustrated how the chlorine or hydrochloric acid or how the sulfuric acid uh, emerged into the structure. Okay, This is, I think, all for today. Thank you for listening with us. And these are just simply illustrations. This is addition of water. This is addition of halogen. I had given you a lot of examples to this because or you cannot understand the different mechanisms or addition mechanisms for alkynes, our next topic, if I will not give you a drill or a repeating explanation of the slides through this explanation. So please master or understand that well about addition. Anyway, the addition that organic Chem 1 will share to you are just simply addition, addition through halogenation and the active role of Cl, sulfuric acid, bromine. These are just simply the things that are supposed to be known in the preparation or reaction of alkenes. And then this is the Markov-Nikov's law. We have also common postulate, but this is just simply to tell you that organic chemistry does not stop in organic chemistry, but also some of the theories here could be used in your physical chemistry. Okay, hydroboration, meaning the addition of boron. So the boron here, BH2. One of the H will be working with the other end of the double bond. The remaining boron and hydrogen, that is hydrogen 2, will be going to another side. And that is the product, the alkyl borane. Okay, practice. These are just all practice. This is a practice on hydroboration. So the first part is on addition and then Markovnikov's and then hydroboration. Okay, that's all for today. Um, Next week is your midterm exam week. So you review from the beginning up to alkene. But how I wish that before the midterm, uh, we have finished the hydrocarbon. So maybe you will have your midterm exam on the second day. So that is Thursday. So by Tuesday, we will be discussing the different alkynes. So I want you to review. I had added extra or repeated illustration of slides to explain to you further the different reactions. Okay, bye for now. So again, I repeat, you review.